Hello, folks. This is one of our unplugged, off-the-cuff conversations with Professor Gary Marcus. If you like content like this, please consider hitting the subscribe button and also rating our podcast on Apple Podcasts. Enjoy the show. So let's be honest, folks. Professor Gary Marcus needs no introduction whatsoever. This is his third appearance on the show, a feat only matched by Connor Leahy, someone on the diametrically opposite end of the spectrum from Gary. Professor Gary Marcus is a cognitive scientist. He founded Robust AI and also the machine learning startup Geometric Intelligence, which was acquired by Uber. So after that, he was a director at Uber AI Labs. He's the author of 5 books, including Rebooting AI, and he's Professor Emeritus of Psychology and Neuroscience at New York University. Gary obtained his PhD in cognitive science from MIT, and as we've discussed previously, he advocates for a 4-step program, the initial development of hybrid neurosymbolic architectures, followed by construction of rich, partially innate cognitive frameworks and large-scale knowledge databases, followed by tools for abstract reasoning over such frameworks, and ultimately, more sophisticated mechanisms for the representation and induction of cognitive models. He thinks that effective cognitive architectures are likely to look more heterogeneous with many specialized modules. Anyway, Gary, it's an absolute honor to have you back on the show. Welcome.
Thanks for having me back.
Amazing. Well, I want to get straight to the meat of the conversation. Everyone wants to know your take on Ilya Sutskever and the slightly conscious language model. I mean, one day we hear they hallucinate, and the next day we hear they're slightly conscious. What's your take on it?
I don't see the argument at all for them being conscious. I will pause and say that nobody really has a consciousness meter or a good definition of consciousness, and so it's like pornography. I'll know it when I see it, or something like that. We don't have a clear definition. However, by any of the criteria that I think are interesting, I don't think that it particularly qualifies. So there's no semantic grounding in anything. There is basically just kind of statistic mongering over large scale data. There's no real reasoning over anything, certainly not in a reliable sense. There's no coherence. And I think you could argue that consciousness is about forming a coherent representation of reality, and it doesn't really do that. And I mean, really, it's just matrix multiplication. And I'm not sure why one set of matrix multiplication, possibly a larger set than somebody else did last week, should suddenly magically cross the threshold. So, I mean, you could still take a very panpsychist view. The most extreme would be like rocks are conscious, and then, okay, maybe, all neural networks, in fact, all computer programs are slightly conscious. But to the extent that the conversational implicature was that there was something surprising about its consciousness relative, alleged consciousness relative to any other system, I just don't see the argument.
Are you a computationalist, by the way?
Well, I guess, again, we're going to need a definition for that. What do you mean by am I a computationalist?
Well, do you? I mean, like substance dualism is when it's about the irreducibility. So whether you think that the mind could be kind of like composed entirely of its physical circuitry and components.
I mean, I like the phrase that the mind is as the brain does. I think that, whatever our cognitive systems are a function of the brain. And if you want to be technical about it, the spinal cord, and you get, you have nerve sensation from all over the body and interesting things going on in the stomach. But I think that basically the stuff that we call the mind is somehow physically realized, for sure. And you can take a kind of functionalist view and say that anything that did the same computations would, in some sense, have a similar kind of mind. And, I think those are reasonable arguments. I think a lot of these arguments suffer because there are no hard definitions that they're grounding out in. And so, ultimately people can have different definitions. I mean, take the word symbol. Maybe we could talk about that too. There are 40 different definitions of symbol, and whether something is a symbol system partly depends on, what do you mean by that? And where do you want to go with it? And when it comes to consciousness, you could take different kind of views about functionalism depending on what your definition of consciousness is. And so it's very hard to ground yourself in a fact of the matter about these things. You can ask maybe more specific questions like, is a particular system self-aware, right? Which I left out of my litany before and shouldn't have. I could make an argument that the GPS system in my phone is aware of its position. And therefore, when I ask it, how do I get to, the east side of town, it It makes a computation based on its current representation. So it's self-aware of where it is in the physical world and makes good choices, not perfect, but pretty good choices about taking left and right. And in fact, it's able to hook up to the web and integrate information from the web. Well, GPT can't do that. GPT can't look up its position with a GPS, can't put that into a computation, can't can't build a representation of where it is in the world, make decisions accordingly in a real world. So, maybe my GPS system is actually more aware, has more self-awareness than anybody's large language model. As they used to say, put that in your pipe and smoke it. I mean, it's I say it half in jest, right? I mean, I don't really think that I want to attribute self-awareness in the sense that I mean it in consciousness to my GPS system, but that is actually an element of what you need is you have to know your position in space and time. Lots of robots have that, and lots of cars nowadays have that, but GPT-3 doesn't. So, why does it qualify?
Right. Yeah, I think the example you gave of the GPS, that's analogous to the kind of parlor trick you're talking about with GPT-3. But we spoke with Professor Carl Friston earlier, and he was saying that for a system to exhibit intelligent behavior, it needs to have a kind of reflexivity.
Consciousness, not intelligent behavior.
Well, he started by saying intelligent behavior. It needs to be a part of a closed loop, which means that, we were talking about just the brain, but it needs to be embodied in some sense. There needs to be some slightly zoomed out and reflexive process.
Well, so I don't think, GPT qualifies for that. I'm not sure that my car example really qualifies for that in terms of the zooming out that you're just describing. So what the car navigation system can't really do is to reflect on the fact that it is a car navigation system, that it's inside of a car, and it probably will forever be unless somebody performs a transplant operation. I mean, there's some level of reflexivity, if that's the right word, reflectivity, I'm not really sure the right word here, that a human has, for example, and maybe not too many other creatures have. And clearly GPT does not have this, and I don't think very much software at all has this. There are some software systems that can do some self-checks and self-diagnosis and stuff like that. You could maybe attribute a little bit of, probably what you really want to do is to say that there's a bunch of necessary conditions. We don't really know the sufficient conditions, and we certainly won't know the sufficient conditions unless we give better definitions of terms. And then on those sufficient conditions, we can say, well, can a system represent where it is, for example, physically? Can it make decisions around that allow it to use that for something functionally? So maybe if you literally just have the GPS without the navigation stuff, the turn-by-turn stuff that I'm kind of putting as part of the example, maybe that's part of it. But, until you actually use that to make a decision, should I go left or should I go right in order to get to point B, that's, a lower level or something like that. But, we probably don't want to wind up with a conclusion, even that the fanciest navigation system, the Waze with traffic recognition or whatever, probably still don't want to argue that has self-awareness. And, something else that you and I have talked about is the sociology, I think, of AI right now. The fact that Ilya Sutskever said this about GPT, well, I could have said that about Waze, and it would have been ridiculous and nobody would have picked up on it. But because of, the power dynamics of Silicon Valley and blah, 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 one of those comments would get picked up and the other probably not. So, I mean, I could, for fun, at least make the claim that Waze is at least a bit closer to consciousness than GPT-3. And I do not see the argument.
So that's a funny point, but I guess you said that software is not conscious. There's no software today that's conscious. Agree with that, but will it be possible, just to narrow down a computational, framework, will it be possible in the future to have software running in silico that's conscious, or is there some barrier that will make that not possible?
Again, it really depends on your definition. I think the closest thing that we've got now are robots. And there are lots of different robots. But let's take, a Boston Dynamics robot, since people know them, like Spot. So Spot has some representation of where it is. There's I don't know the current state of the software, but, I saw it a few years ago, and, there's some degree to which you might be able to set it to do certain things autonomously. And, so there's a recognition of awareness. It has set of decision-making things around that. You could, if you really wanted to argue that something out there was conscious, then, maybe that would be closer. But in other ways, you'd say it's really unsatisfying. It doesn't have any ability really to reflect, for example, on its goals. The user sets a very narrow goal and it pursues that goal. Like, I don't know the current state of the software, but let's suppose you can say, I'm in this part of the room, I want to go to that part of the room. In that sense, it's not so different from the driving systems. I don't see more than that. I still don't see what we're getting at with consciousness. Like, I think that whole field has problems. And the number one problem is there's no gold standard or gold truth as people would talk about it in machine learning. Mostly we just have, I think I'm conscious because I said so. And then, like, paraphrasing Descartes, a little more in your face version of Descartes. And like, we don't get very far after that. I'm guessing you guys on the call are not deep fakes, that you are conscious, but what do I know? I'll tell you a favorite quote, by the way. Raymond Smullyan was a logician, wrote some great books. And he had this line about solipsism, which is like this idea that you're the only person that exists. Or I am, really, be my idea of solipsism probably, that I just expressed. He says, sure, I'm a solipsist, but then again, that's just one man's opinion. So,
right. Yeah.
How do you get past that? How do you establish ground truth? So, like, a lot of people would probably think that their pet dogs are conscious, and maybe they're right and maybe they're wrong. And like, if I can't answer that question firmly, how am I going to answer the question about whether Spot, which looks a little bit like a dog, is conscious? Like, I can start to make some systematic claims. I think there's a lot of things dogs can do that Spot can't. There are probably a few that Spot can do that the dogs can't. Now I need some criteria. And Ilya is not a philosopher, did not offer any criteria. He just said this wacky thing.
And do you place weight on the importance of phenomenological experiences, like the qualia, or do you have more of a declarative notion of consciousness?
You should have warned me you're going to talk about consciousness, so I could have brushed
Oh, no,
out.
so we don't need to talk about it.
Fine.
We can talk about anything you want.
I'm just kidding you. I always like to improvise on whatever people give me. But I would say that we have not a lot of clue about what qualia are. But there's a real argument that there's something there that is to be understood, even if we don't understand it. So, like, what is it like to feel like red or to experience an orgasm? I'm going to guess that GPT has neither of those feelings, and I don't see any particular reason to think that it does. Its ultimate incoherence is one reason to think it doesn't, right? There are other reasons to think it doesn't, but if you really had a qualia of, like, let's say feeling like a person, and then I ask you, are you a person? And then I ask you, are you a computer? You should give different answers because you have some inner sense,
right.
phenomenological sense of who you are. But I guess I can give a little hint that I'm involved in an art project in which I ask GPT exactly that. Are you a computer? And I forget the order, but ask both those questions. Are you a computer? It says yes. Are you a person? It says yes, like immediately back to back. And, there's no stable representation of anything. It's not really, in fact, drawing on an inner state at all. And actually, as I think about this online, an important part of consciousness for a person, I would say, is having a cognitive model of the world. It doesn't have to be perfect. Our models of the world are not perfect. And one of the deepest questions deepest things that philosophy teaches us, I think, is that we live in our own reality. We don't have direct access to external reality. All of our representation of reality is mediated through our senses, and everybody should know that if they're talking about these questions. But what I think follows from that is that you do have a reality that you have constructed, and that's really pretty critical. And it tends to be, at least for people, a stable reality. It's not perfectly stable. So you can get things like Necker cubes where your inner representation of the outer reality actually flips, right? It's not stable. And you can have other things, it's a bird, it's a plane, it's Superman. And so you change your mental model over time of what that flying object is. And that's not uncommon. But there's a lot of stationarity to our mental representations of the world. And I think that's part of consciousness, is having those relatively stationary representations of the world. They're always subject to update. So, you're playing a prank on me. It actually is deep fake stuff that you recorded, and now I'll have to deal with that. And you can tell me that. So it's possible to change the mental representation, but we have a process of building a representation, and this is, in my own words, my own way of presenting it. It's very similar to some things that Dennett has said about like the theater of consciousness. So you have this inner thing which you can do computations over. So you have a stable representation. This goes back to the introduction. You said I'm someone who emphasizes cognitive models. This is what I mean by it is you have a cognitive model. So like my model right now, I don't know how you'll present this in your video, but right now I have a model that says I'm sitting, in a room, there's a desk there. On top of it is a laptop. There's a camera pointing at me. I see videos of 3 different people. I don't know if your viewers will see that. You're nodding your heads, which means you understand what I'm saying. I'm trying to communicate something. If you don't nod your head, I'm probably going to try to repeat it and say it in a different way. And I'm modifying that over time. Like, are these guys on my side? Are they skeptics? Should I be worried about what they're going to put out there? Right. So I'm iterating on that model constantly. Same thing if I watch a movie. Like, I just watched this Netflix series, the title, which I cannot fully reconstruct, but stars Kristen Bell. And the whole thing is about constantly changing your mental representations. Like, who's the bad guy? Is she hallucinating? Is she not hallucinating? What's her mental state? It's kind of about an unreliable narrator sort of thing. And so the whole fun of watching the show is you are building a mental model. You realize that the show has been designed to keep you on your toes and you're going to change your model. But that model is your conscious representation at any given moment. So it's, 8 episodes. I'm embarrassed I watched them all. And, so like when you're at the end of episode 2, like you have a different mental model of what's going on watching that. And of course you do the same thing in real life. And I think that that's pretty important to consciousness. And there's no way that any large language model really does that.
That's fascinating. I mean, first of all, Gary, have we ever let you down?
You have.
You can trust us.
My mental model on you is firm, but life is, maybe you got a bribe.
Exactly.
You can always elaborate circumstances. No, but you've been good to me. That is part of it.
Indeed, we have. But no, actually, Tristan was saying something very similar earlier. So when he started talking about consciousness, he was saying that, well, actually, there's a kind of predictive way of looking about it. So you can have a theory of mind, and you can kind of do planning and think about trajectories in the future and how other people will respond to those trajectories. And that's something which is constantly evolving.
You pause there for 1 second and then you can maybe finish the question. So I was just emphasizing the model in terms of like the current states of affairs. And then I would say theory of mind is like, a set of mechanisms, and nobody really knows, but a set of mechanisms that then allows you to make predictions across that current state of affairs. And that includes some long-term stuff. Like, I don't think you took a bribe, but I know sometimes people do. And so that's part of my general common knowledge. And so, I assign a very, very low probability to it, but not 0 in this crazy world in which we live, in which, Republican Congress people suddenly change their minds about certain things or whatever. So, there's actually multiple steps there. That was more what I put under reasoning in a very generic sense in the article that you were kind of alluding to, the next decade in AI. So there's this, it's the lines between these are gray, but roughly speaking, we have a set of knowledge. We have the background, long-term knowledge. We have some kind of knowledge about the current situation. I mean, really the current situation probably is like a cognitive model of your whole life and your history and whatever, but there's like general knowledge. There's knowledge that's particular to you. Sometimes people talk about procedural and declarative knowledge and so forth. And then there are also mechanisms of reasoning over those things. And that can include deduction, induction, abduction, which is like inference to the best explanation. So when I make an inference in theory of mind, I've got like some knowledge from a cognitive model. Like I'm talking to you right now, that's part of the cognitive model. I'm gauging your reaction, and I've got mechanisms for like reading your facial expressions that feed into other things. Like I'm trying to model, do you understand me right now? Right. I mean, part of the skilled teacher or lecturer or podcast guest is to get that feedback. It's why it's harder to do a strictly audio podcast than one where you can see the other person. And it's why I hate doing Zoom calls where everybody's got their camera off. You can't get that feedback. So you don't know if you're doing a good job or what's missing or whatever. So you're integrating all of that stuff in a good cognitive model and then making all kinds of inferences. Like, okay, now I think you didn't understand. I'm going to pause. I'm going to try to explain that piece again, etc.
That's fascinating. I mean, I think there's two places we can go from here. I mean, I was going to bring up ELIZA, and I mean, Melanie Mitchell
Obviously
talks about
conscious,
wishful
right? Eliza,
mnemonics.
conscious. It says things
Well,
in response that are vaguely relevant to you. So, I mean, we've had conscious computers since 1965. That was said tongue in cheek, right? I do not think Eliza is conscious. That was a joke. But I mean, by what criteria, right?
It's a very human phenomenon. I mean, the chief scientist at OpenAI could be forgiven for thinking that it's slightly conscious, but it is a very human phenomenon.
In rebooting AI, we talked about, I think the phrase was the gullibility gap. And we actually used ELIZA as an example, but GPT-3, which didn't exist yet, would fall into the same thing. The point of the gullibility gap is we're not evolved to be able to distinguish machines from people, right? I mean, that wasn't part of the environment adaptation. There was no such problem for our ancestors. And most people are not trained to do that. And so we can take a small amount of intelligent behavior and essentially we assimilate people into the set of human beings because there's no other creature that can do those kinds of things. So your dog cannot do what ELIZA does. I mean, ELIZA is actually not nearly as smart as your dog, but it's easier to trick somebody with ELIZA into thinking, because it's linguistic in some sense, right? Everybody in your audience, I hope, knows about ELIZA. You say, how am I doing? Or I'm feeling sad today. And it says, tell me about your family. So like that one little bit of contingence, like your dog is never going to say, tell me about your family. And so people can get suckered into it. Another example of the gullibility gap is for years, people have thought that driverless cars are just around the corner because they don't really understand the nature of reliable ones that we could actually use that would actually be level 5 and take us from point A to point B. So we've had some version of driverless cars since like the 70s or something like that. Forget when somebody first took a car on the Autobahn and, every time there's progress, people get really excited, but it's a version of the gullibility gap because you see a little bit of illustration of a behavior that's very human-like, right? Again, your dog can't drive your car, not on the highway, not for 1 minute. Don't try it at home, please. But, you get this software that does it and you think, well, if it can do it for a minute, wow, that's so impressive. It's so different from the distribution that I expect from my dog and my cat and my baby. That there must be really something there. But if you actually understand the problem, you realize that there's an enormous gap. Elon just tweeted about this yesterday about how hard a problem is. And the reaction from the rest of us in the community is like, I know, right? We've been telling you this for a long time. I haven't decided whether to post my receipt, so to speak, but I have a long discussion of this on The Edge in 2016. Maybe you can link it in show notes, where I talked about why driverless cars, even though we already had examples of it in 2016, is really hard because we have this outlier problem. So it turns out that it takes a special kind of mind to be able to deal with the outliers, namely one that can build a cognitive model of where it's driving. And we don't have that for the most part, a little bit, but we don't really have full-scale cognitive models. So, for example, Elon's system, somebody who posted this recently, would otherwise, without intervention, drive into a human being holding a stop sign on a pole, right? If someone actually had to slow down a car that was running into a human carrying a stop sign on a pole. Well, there's no cognitive model, or not a rich enough cognitive model in the Tesla FSD to be able to recognize that that is a human carrying a stop sign. That's not something it even knows how to represent. You represent it. I just said it. A person carrying a stop sign. Now you can visualize it. You can go look at the picture and see how close your visualization is. I could try to embroider it or whatever, and I could tell you that, the human was wearing yellow or whatever. So you build a cognitive model that is compositional. It's a whole that is unusual, consisting of parts that are not unusual. Actually, the stop sign that's not in the ground is a little unusual, but you can imagine, you pull out the pole, you got the octagon. Okay, I get it. Looks like a big lollipop, right? And you got it in your head now. So you have this big lollipop, somebody's holding it. Now you have a cognitive model of that. Well, I'm willing to bet that at least until, maybe they dealt with that outlier case now, but at least until a few weeks ago when this was discovered, there was no way even to represent in the system the possibility of somebody carrying something. In fact, the whole verb carry probably isn't represented in the limited repertoire of the thing. There are some things in its cognitive model, like roads, but not a lot more. It's not rich. The thing about your cognitive model system is it's incredibly rich. Like I have some headphones here, and this is a made up example, but if you had never seen folding headphones before, then okay, immediately you would construct a cognitive model. Okay, so now there's a thing is folding headphones. Probably I had never seen such a thing until X years ago. And then I saw one and I was like, yeah, that'd be nice because I could stick it in my backpack. You were immediately able to make the inference that I could stick it in my backpack, even if you hadn't seen one up until that point.
I have a question because you're hitting on some really interesting things. So first off, I think you would agree that whatever models, whatever world models human beings create, they create abstract world models. Is that fair?
Yeah, I mean, there's probably a mix of abstraction and, very concrete stuff. So,
Okay.
I represent this room in very abstract ways of like, there's a desk and I can raise and lower it. And then there's specifics like right now it's at, 42 inches high or whatever. I mean, I'm not that precise about it, but this is not a perfect example. But, we're capable both of representing abstractions, like there exists a class of things that are folding headphones. And this is another really important thing is types versus tokens. These are my headphones and I don't want you to wear them because, I don't want your cooties. And so I'm going to track mine.
No, I get that. But I think where I'm going here is that because the compositional models is what I wanted to ask you about, because in my mind, at least, and what we've seen so far is that abstraction is the key to building those compositional models, objects that can be placed together, et cetera. And we were talking, as you know, with Yoshua Bengio, and you haven't watched that episode yet, but a big part of it is about these G-flow nets. And his argument there is that if you have a compositional tree, a flow net, and then you take a neural network and attach it to that so that it can learn flow weights such that it generates a generative model that is recapitulating, some reward function or the real world, that this is really a step towards the ability to learn abstract models. And I'm just wondering, I mean, given that there are caveats here, I'm just wondering what you think about that approach of really trying to learn compositional models that in a sense are abstractions of real world, world.
I can't speak to the details because I haven't read the paper yet. Though it sounds interesting. Is it published yet?
Yep, it's published.
So I need to read the paper before I say too much, but I will say that the abstract characterization of what he's doing, I think, is both right and a step towards neurosymbolic cognition. And it's taking a playbook that is very clearly understood in the symbolic world of constructing wholes out of their parts. I don't understand the technical details of how it's done, but that and Glom are both trying to build, Hinton's and Glom are trying to build wholes out of parts. Now, Hinton's model, when I looked at it in detail, really seems to me to be a symbolic model that isn't called that. So in particular, what's really driving it is creating symbolic representations of the parts, which are called embeddings, but are intended to be stable across context. And that's really what a symbol is. So you can think of like, the ASCII code for the letter A is a certain, bit string that is stable and universally used as a code. And that's the foundation for modern computers. And I think Hinton's sort of backing into doing exactly that. I don't know in the technical details of how G-flow works, for example, what the wholes are and what the parts are and what the relations are, whether you wind up with tree structures that you can traverse, which would be, the kind of classic symbolic thing. So you could imagine, for example, that you sort of have a symbolic version of all of this, but you can do some interesting differentiation across that, and that could be interesting. What I've always been committed to is that you have to actually be able to pull out the parts from the whole and be able to analyze what the whole is in terms of the parts. If he can do that in an innovative way, then great. If he can't, then I think we still have a problem. And, it has been a problem with a lot of the other literature in neural networks that you can't really do that. So there are a few representations there, tree RNNs and stuff like that, have had explicit representations of trees and things like that. But by and large, or a typical thing is like a large language model where you can't recover the parts. So I was playing yesterday with something called Proofwriter, which is a really interesting system by Peter Clark and some other people at Allen AI. And sometimes it does very well, and other times it does pretty poor. So I took a example from the entailment literature, which is like Ames is a clever spy. And then you ask it, is Ames a spy? And you should be able to make that inference. And it says no. And, I don't know exactly why it said no. And the kind of hallmark of these systems, you never know. This one's actually better at being able to list intermediate steps in its inference, but you still don't really get a sense of why it failed on that. If you had a proper compositional system, you should be able to derive that.
Yeah. And so can you help me understand why is it so important to be able to recover the parts? Because, for example, in neural networks, they gain a lot of their power by being able to do, if they have power, by being able to do this entanglement, right? Where they can kind of share representational states across different, and I'm going to use the term loosely here, categories. But I'm just wondering, suppose I had a system, and let's assume that it isn't just a matter of definition to be compositional, that you can recover the parts, but what's the practical importance of being able to recover the parts?
So let me first insert, sharing is good. I mean, you want to have representations that you can share across systems. I mean, in the old days of neural networks, there was no sharing of anything. And then people figured out like how you could at least like take off the last layer and put on a new last layer. And so you're sharing the internal representations. Sharing is good. Of course, symbolic systems are all about sharing. I have some common database store, and then I have APIs that can call it and so on. There is no way to AGI without being able to have shared representations. And Hinton's GLOM is another approach to shared representations. So that part is essential. It's necessary on anybody's approach. And I think without it, we're in trouble. So then the question is like more like interpretability and recoverability. And I think I just gave you an example. So if I read the sentence, Aim was a clever spy, I should be able to now tell you what he did for a living, right? I should be able to, if he's a clever spy or a lousy spy, either way, I infer that he's a spy because the sentence structure of it is Ames, let's say the sort of Chomsky analysis, Ames was, and then we've got a noun phrase there. And I don't know, the head of it is spy. There's different ways to talk about it. There's an adjective modifying. If I have that structure, then, on any reasonable semantics, it falls out that Ames was a clever spy. Now, another place where this really matters, and nobody has a good solution kind of on tap, is negation. So these systems, Alison Edinger did some nice work on this. Some other people have. Hers was with BERT, but it's still generally an issue. If I say something like John is alive and John is not alive, you should understand those as really being different. And you should be able to derive that from the compositional structure and from understanding quantifiers and negation, words like not. If all you have is a whole, then you can wind up with weird phenomena. Like the sentences John is alive and John is not alive might be closer together in space than those two sentences are to John eats jelly beans. But you want to actually be able to have a system that's so clever that it can infer from John eats jelly beans that he is alive, and can infer from John is not alive that the sentence John is alive is false. And you need to have some fluidity about working across those parts.
Well, I wanted to put something to you, Gary. So one thing we've been thinking about, we had a wonderful conversation with Randall Balistriero, and he painted this picture of neural networks as being a little bit like a decomposition method. So you decompose the Euclidean ambient space up into these little polyhedra, and all of the neurons basically form faces of the cells in that polyhedra. So it's that you can kind of think of them as locality sensitive hashing tables, much like many other machine learning algorithms like decision trees also carve up the input space. Nearest neighbor does as well. So that's an interesting first thought. And then the second thought is, well, how do they extrapolate at all? Well, inductive priors, essentially, they create space junk. They kind of replicate copies of the information all over that ambient space, so it becomes interpolative. Data augmentation does the same thing. It's creating more space junk. So the difference between reasoning as we know it, Gary, and the neural network seems to be like reasoning I think of as being a kind of search or discovery process, and neural networks I think of as being more of a memorization process. And we can only cheat by kind of creating this space junk all over the ambient space. I mean, is that a good way of thinking about it in your view?
Well, you can certainly think of reasoning as a search process. What to me is essential is that it's an algebraic process. Let me come back to that in 1 second and first say, yes, I think the neural networks are basically memorization devices. They're not literal direct table lookup. They're much more sophisticated than that. But like there's a really nice result. I wish I could say the first author's name that I tweeted about last week, maybe put it in the show notes, that looked at arithmetic. I think Samir Singh is the senior author on this paper.
I've invited him on. He's coming on in a couple of weeks. Can I just frame that up actually, because that's beautiful. Yeah. After our GPT-3 conversation, we had this notion in our mind, didn't we, Gary, that it's just memorizing the input data, and the folks said, oh well, look, it's memorizing. It's producing really good results one shot on these multiplication tables. But what these folks did, now that GPT-J has been released, the data set is publicly available. So now you can do some really interesting lookups between multiplication results.
Let me just insert. It's Eleuther's data, not GPT-3's data.
That's right. So it's GPT-J released by Eleuther. Exactly, but it's a wonderful situation that Eleuther did release their data.
Exactly, it's fantastic.
So when you plot the accuracy against the occurrence statistics in the data set, it's a linear graph, and then they just changed. So the x-axis was the second component of the multiplication, and you would expect similar numbers to be very close together on that graph, but they weren't. They were very far apart, which was, I think, very strong evidence that the model is just memorizing the data set.
Exactly. I thought that was a really important study. I tweeted it as, super important. And I mean, there are other things that have pointed in that direction. And in fact, I anticipated this years and years ago. If I have a chip on my shoulder, it's that in 1998, I said these things are basically just memorizing and not extrapolating. And I was attacked, I may have told you this before, for somebody characterized that as a terrorist attack on connectionism. Pointing this out, I used an example of the identity function to make the point. It's very actually similar to the recent result. And that hasn't changed in 20 some years, and people should, anyway.
I know, but I wanted to put another thing to you, because we were talking about self-driving cars earlier. And to me, it seems completely obvious what we're talking about. When you have this open-ended domain and you have a combinatorial explosion of possible compositions, you have all of these low-frequency attributes, if you like, on the long tail. You're literally trying to memorize infinity.
Yeah. I mean, look, it's an empirical question. With driverless cars, it's an empirical question. It might not be infinity. It might be some very large number. And I wouldn't want to say there's no way it's going to work, but, empirically we can see that throwing more data is not really fundamentally changing the outlier problem. So, it's a large number, it's not infinity, but it looks to be really, really large. And, it's not clear that the scaling works. We could talk about scaling laws in a second. I've been thinking about a bunch of them, but let's go back to the other question, which is, what is the reasoning stuff, and why do I call it algebraic? Even though there is an element of search in reasoning, right? You're searching different ways you could prove something. That's very valid. But the part that to me is even more core is the extrapolation is algebraic. So what I mean by that is you have a rule in algebra, like y equals x plus 2. So you have a variable, or actually two variables, y and x. You have operations plus and equals, and then you can substitute arbitrary things into your equation. So I think I said y equals x plus 2 maybe was the thing. So now if I make x 5, then I can calculate for y, the corresponding value. And I can do that over an infinite class of some things. So I could define it to be over integers or real numbers or, what have you. But that's how algebra works. And I think that's how reasoning works, is you can do things over essentially unbounded classes. Like this is going to be true for all animals or all people or all left-handed people or whatever. So you have some class that you're bounded to, and then you can do it across all of them. Multiplication is like that. But in the system that we just talked about, GPT doing multiplication, you don't get this phenomena where I can do it equally well for all instances of a class. You get something where it's very similarity dependent. My graduate school work with Steven Pinker was about language and had exactly the same phenomena. We looked at irregular verbs and regular verbs. And what we found was that children's over-regularizations for the irregular verbs were very dependent on frequency. But if you gave them, the correct irregulars were dependent on frequency, but they could over-regularize anything of any sound because there was a general rule that could operate freely. Is these rules that operate freely that you don't really have a clean representation of in a transformer model. In a transformer model, you tend to emulate them. So you emulate arithmetic with respect to the known cases and cross your fingers for the rest. Well, can you imagine me shipping a microprocessor where you had to cross your fingers for some multiplication problems like this? People think about the Pentium and they got all upset that there was a bug, and it's right. 1 in a trillion operations was off by a bit or whatever. And then you've got this thing that's off half the time on ordinary arithmetic. And you have $100 billion of research funding in the thing that's wrong half the time on, most arithmetic problem. Like,
so let me, okay,
explain me
but
that.
I want to dive just a bit on this extrapolation versus, I'm assuming the opposite of that is interpolation. Because we did have, as we mentioned, Ian LeCun and Randall Balistriero on, and they made a point, which in some ways is very compelling, which is if you define extrapolation kind of in the very classic linear way, which is that, if I've got all my observed data, there's a convex hull that contains all that data. And if a new data point is outside that convex hull, by definition, it's extrapolation. Okay, they go from that, and I agree that's kind of perhaps a naive definition of it, but it's a definition. If you then add in the curse of dimensionality, so now you have, 1,024 dimensional data because it's images or something like that, it's almost always going to be extrapolation. You're always going to have data points. The new data points are going to lie outside that convex hull. And they made the argument that, hey, this means neural networks are always extrapolating, and look how well they work. So I guess my question to you is, what's a more useful definition of extrapolation versus interpolation that doesn't just fall apart in very high dimension?
I'm not sure the perfect definition there. The first thing I would say, though, is the old Groucho Marx line: who are you going to believe, me or your own lying eyes? If you look at what these systems actually do, they're clearly still struggling with extrapolation. So, like, for example,
Right.
Proofwriter, it works up to a point. Or, for example, the multiplication system from Samir Singh's lab.
Right.
Same thing. It works up to a point, and it's clearly not. So, like, empirically, these systems are not extrapolating. And there's an important point here: the function that a person would be extrapolating.
Yeah, so they're not. I don't think they're extrapolating at all.
Well, but I'm asking for a definition.
If you look at the convex
again,
hull notion,
there's some room for definitional haggling, and I have to think about their definition. But when it comes down to it, what I'm interested in are these operations that people can do fluidly. I mean, multiplication's not perfect because people actually have some trouble, but certainly that machines in principle could do fluently. So, there are tens of billions of pocket calculators and computers that can perfectly extrapolate the multiplication. And they're not even doing it as extrapolation. They're just defined to do it over a full class.
It's exactly, but Gary, that is performing a computation. Neural networks, as I was just saying, there are inductive priors, and it's their responsibility to create space junk everywhere. So even if you wanted to extrapolate the sine function, you would need to create an inductive prior to basically create space junk outside of the training range. It would be specific every single time. So the CNN prior creates the space junk everywhere. There's no way of doing it without creating the space junk.
I mean, that's their only means, right? They use what you're calling space junk to kind of emulate functions, right? And they invariably, well, that's probably too strong. In many, many cases, the space junk strategy doesn't really suffice for outlier cases. When you compare it to a microprocessor doing multiplication, there is no notion of an outlier case. It's just, within these bounds, I will get the right answer. And this is why you want some things to be done with symbolic operations, is because you can define them so that you're not at the mercy of, in my training set, I happen to have this example. One of the reasons I love what Aloyther is doing is because exactly these questions need to be answered. How much is memorization? How sensitive are you to the training set? And the Samir Singh study is, a good example of that kind of test. And, the answer is pretty clear. You can see it on the other end. The people are talking about now the data leakage problem. Well, the data leakage problem is basically the system is mimicking, your credit card number or whatever it finds in the database.
The background of a cow. It finds everything with grass as cows because all the cows had a green background.
I think that's a separate but related kind of issue. And I love the snowplow, the school bus in a field of snow that they describe as a snowplow. And I mean, there it's what it's telling you is that what the system really cares about is a texture, not the abstract concept that a person would care about.
So you mentioned earlier you had some commentary on scaling laws, I believe.
Yeah,
could you go into that?
Yeah. There was this very clever paper by Kaplan et al. At OpenAI that's, I think, gotten a lot of people excited, which says that there are scaling laws for large language models. And I think there are a few remarks to make about them. mean, first, what are they for your, in case your listeners or viewers haven't seen them before? They're these nice, neat lines. The original ones were showing, the bigger your model, the better that you're able basically to memorize the training set. It didn't use those words.
Right.
But
Isn't that pointing out the obvious?
It was, it could have turned out that you might not have found that. Like there'd be a saturation function. That's actually part of what I want to talk about. But
well,
so
could you comment on that though? Because we said there's this combinatorial space of possibilities, so it's not going to saturate, is it? Have I understood that correctly?
I don't actually quite know the limits. And there's some interaction with data and having enough unique data.
Is the saturation limited by the training benchmark?
No, there is no saturation. So on the training set,
on those original results, there was no saturation.
Yeah. Well,
that's right.
So in the original, just so everybody's on the same page, there was no saturation. There were nice clean functions where you could basically predict things. And there've been a bunch of things like that. But here's what they left out. Well, actually, first let's talk about a rhetorical trick. So they call them scaling laws. They're not actually laws. They're not laws in the sense of laws of the physical universe. They're really empirical observations that have held under some regime for some task.
Right.
And then that raises the question of under what other regimes and what other tasks. So, mastering your training set is one thing, but generalizing on some other task, let's say about common sense, is another. And, we're already in 2022, and there's still, bigger models to be made, finding some evidence of saturation where some of the models reach a point of diminishing returns. I saw evidence of this on kind of moral reasoning task from Anthropic that was just published. DeepMind has some papers recently that kind of point in this direction. And then there's also, they used to call it décollage in the Piagetian community when things separate. So, and it was a kind of embarrassing thing to admit in the Piagetian community because it was supposed to be everything moved in stair step. And so when something didn't, you had to say, well, that's décollage, whatever that meant. It really meant my theory is wrong. And so there is décollage here. So some tasks really are scaling and others not so much. Nobody has the perfect comprehension task, but I would say if we did, I think it's hard because it would require a lot of hand work by humans. If we really had a task, does this system comprehend things? I would say there's been, at most linear increase that's very, very modest. And we're basically on the floor still in terms of having a system actually understand language. That's not scaling anything like the rate of memorizing a training set as a function of model size. So there's already evidence that common sense is not really improving at the same rate. And, AI safety is measured in various ways. It's not really scaling at the same rate. There's evidence that some things actually get worse, like bias in one of the senses in which we use the term may actually get worse, get bigger as you scale the model. And the problem with bias is you're perpetuating past history. So you get better at perpetuating the past history, but that's in opposition of what you actually want to achieve. You want a just society that doesn't just perpetuate past history. Maybe that's too much of a digression, but the bottom line is they're not absolute laws. It's kind of like, Moore's law was operating for a while, but some people think in the last 15 years it's slowed down. Just because it's true for a while doesn't mean it's true forever. And even if you made some argument that Moore's law is still operative, nobody thinks it's going to go infinitely. The way I would put it is there are some things that you would expect the models to get better at. And fundamentally, they're just predicting the next word. And, no surprise that if you give them more capacity to memorize, that they're going to get better at that. The real question is that going to help you on the full range of things that you need to know? And predicting the next word is like a tiny piece of what we need to do for language. The remarkable discovery is that gets you to 80% on a lot of things, but it typically does not get you to 100% on anything useful other than autocompletion. And so all the other things you might want to do, maybe they don't scale as well, and then you might have a problem. So the empirical question here, I think, for driving as an example, is you have a whole industry that's actually predicated on the belief in scaling laws. People didn't make that explicit, but that's been the operative assumption for at least half a decade, a little bit longer than half a decade. And so there's been enormous investment in scaling the data and also in scaling the models. I mean, there are really two things that you could talk about scaling. And the guess that people are making is that if I scale the model big enough and I scale the data big enough, I will solve the outlier problem, right? That's an empirical guess about scaling. And we were already talking about this a few minutes ago. It might not work that way. It might be that there's just too much of a periphery and you start to asymptote and you're screwed. And then, it could turn out that we put in like $50 billion across society on the premise that scaling is going to get you there, and that it doesn't. And we have to go back to the drawing board and build richer cognitive models and who knows what.
I think these may actually just be artifacts of the fact that we're doing all the time the equivalent of maximum likelihood estimation. They're sitting here training neural networks to just maximize the likelihood of a particular class. There's no effort to do any type of marginalization or any type of quantification of the density of the, the uncertain density of those estimations. And I saw somebody, I forget, Tim, what was that paper that had like the super scaling law thing or whatever was that called, where, the longer you trained it,
Grokking.
Huh?
At Grokking, the one where the validation loss suddenly flied up after a long time.
Right. And there's, at least from my perspective, I saw somebody making a very compelling argument that that's just an artifact of the fact that they're not doing marginalization over the predictions, but they're just looking at maximum likelihood. And it's really just...
Oh, sorry, you mean double descent.
Double descent, the double descent.
Yeah.
It's more just a behavior of that particular estimator than it is of anything else. So let me just, I'll make this more precise and give you the reference. So the paper is called Bayesian Deep Learning and a Probabilistic Perspective on Generalization by Wilson and Ismailov. And the point that they make in there was that this observation of some of these double descent or, grokking and things like that are an artifact of the fact that you're finding a best fit model, just a particular neural network. You're finding that best fit model and looking at its behavior rather than looking at the uncertain population of all possible neural networks. And they found that if you do this Bayesian model averaging, the phenomenon disappears. It's like you're just looking at an average behavior versus a maximum likelihood behavior. You get very different scaling laws.
That's interesting. Yeah, please send that to me.
Yep, will do.
Awesome. Well, Professor Gary Marcus, it's been an absolute pleasure. Thank you so much for coming on.
Thanks a lot for having me.
Amazing.